Hey, today I'll be presenting the paper on the distortion of partitioning performance by random quantum circuits that will be published at ICDCS DISC 2026. So let's get right into it. What's the context in which this paper and this research was developed? Well, I work in distributed quantum computing, which is basically a setting where we interconnect multiple quantum devices via quantum network to perform a joint computation that is larger than their individual capacities. Meaning, we take a very large computation, we abstract it to some sort of intermediate abstraction, and then we partition that abstraction in order that so that every device in our network is assigned a different part of this computation to complete so that together they can complete the whole computation because it wouldn't fit in any of them individually. Now, the abstraction that we usually use are hypergraphs. The way we map from circuits, which are one of the most commonly used models of hypergraphs, is by assigning each qubit to a vertex and each gate to a hyperedge. 1-qubit gates would be self-contained hyperedges, 2-qubit gates would be two vertex hyperedges, and then things like the follies or 3-qubit gates in general would be three vertex hyperedges because they contain 3 qubits. After partitioning, we are going to end up with hyperedges or gates that are assigned to different devices. They might have 1 qubit in one device and another qubit in another device. And in order to implement these, we now have to implement non-local gates. Non-local gates can be implemented through multiple communication primitives, and their implementation may look something like this. There will be a pre-shared EPR pair that will enable local computations on both the first and the second device in order so that a gate, such as the CNOT gate, is performed between both devices via a teleportation and a consumption of this pre-shared EPR pair. Now, how do we actually attain these non-local gates or these partitions where we tend to, at the moment, use hypergraph partitioning solvers? Hypergraph partitioning solvers are solving the hypergraph partitioning problem to which the input is a hypergraph. A hypergraph is very similar to a graph, but instead of having two-way relationships where two nodes are interconnected by an edge, they have hyperedges that can interconnect multiple nodes or vertices within one single connection. This is specifically useful for 3-qubit gates, for instance, in the circuit model. Now, the hypergraph partitioning problem is set out to be the following. You have a hypergraph and you want to partition it into different partitions. You can think of them as different QPUs. And each of these QPUs is going to be able to contain a certain amount of qubits. In the balanced hyperpartitioning problem, which is the most commonly used version of this problem, what we want to do is have roughly equally sized partitions assigned to each device. And then the main goal is to minimize the amount of cross-device hyperedges that exist. So of gates that are going to occur between different devices, because as we've seen before, every single cross-device hyperedge is going to have to be translated to a non-local gate, which is going to consume EPR resources. So they cost something at the level of the network. Now, the way we evaluate these hypergraph partitioners, which are in some sense the entire baseline of our pipeline, is by basically plotting the amount of EPR pairs that they consume against the number of qubits that a circuit may have. And we kind of start studying how these partitioners perform at scale, because the whole point of distributed quantum computing is about scalability, and we want to know how these partitioners are going to perform when we are in a reasonable qubit range. So we're talking maybe thousands of qubits. Most hypergraph partitioners today weren't designed for this setting. They were designed for small hypergraphs, so we're currently trying to analyze how they're going to perform at scale. And, as with anything else, the name of the game is, can our hypergraph partitioner be the state of the art in this consumption of EPR pairs, especially as circuits scale in qubit size? Now, the main point of this paper and of this work was to ask the question, or to kind of analyze wherever asking this question of do we beat the state of the art, if the answer to it would change depending on what circuits we were testing our hypergraph partitioning is under. I have this theory that I've been working on for the past few years that I'm continuing to develop, which is that I believe that the structure of partition hypergraphs will lead to some partitioning techniques being better than others over those structures. Depending on the nature of your hypergraph, the topological structures that arise in these mathematical elements, essentially, we will get some hypergraph partitioners being better than others, even though that might not be the case, or that performance might not be equivalent in other types of hypergraph partitioners. So that basically means that choosing representative baselines for our application, in our case distributed quantum computing, choosing representative circuits that actually implement real algorithms, is very important. If this theory is true, it would be a very important thing because it would be a fair evaluation of partitioning strategies. And if we chose non-representative baselines, then it wouldn't be a fair representation because we would be evaluating partitioning strategies against the wrong baseline, and therefore we might get wrong answers. Now, even though this is something that, I consider to be true, but may not necessarily be true, I basically started looking into it, and as I was researching the literature, I realized that a lot of partitioning techniques, partitioners have been evaluated against random circuit or with a baseline of random circuits. The reason for this is very simple. Basically, we don't really have any large-scale benchmarking suits for quantum algorithms or quantum circuits that really reach anything beyond like 130, 150 qubits. So the only way of really having large-scale testing is to test over random circuits. So a lot of people are testing their partitions over random circuits, but what I set out to do is basically to test out if testing of a random circuit was a fair baseline. The experiment went a little bit like this. I created 3 origins, or I decided on 3 different origins for hypergraphs. Some of them would arise from real algorithms taken from different benchmarking suits in the field, so real algorithms converted to circuits. Other ones would arise from random circuits, not fully random in the sense of anything goes, but random circuits that might be output by cascade random circuit functions given different types of inputs. And then a third origin would be generated circuits. So there are programmatical instantiations of well-known quantum algorithms at scale. They're basically these generators that allow you to create, for instance, Grover algorithms at different circuit sizes. So I thought that that would be a good middle ground, perhaps between random circuits and real instantiations of real algorithms. So I took these 3 hypergraph origins, and the name of the game for me was to try to evaluate how partitioner performance would differ, how partitioners would compete against each other against these 3 origins. I chose 7 different partitioners. Some of them were very basic. For example, I just created a random partitioner that would just be the baseline for everything else, that would randomly assign vertices to different blocks. Then I also developed a greedy partitioner, which basically would try to fit as much as it could per QPU, and when it was full, it would go into the next one, and so on. I also chose some more advanced ones like Hyper and Zoltan PhD, which is what I would consider to be the large-scale hypergraph partitioner that is used in industry, not necessarily for distributed quantum computing, but in general for resolving this problem due to its speed. Now, these partitioners were evaluated on different networks. The networks were always fully interconnected, but they had networks that were 2 to 10 partitions, so 2 to 10 QPUs being tested. And what I found was that for a start, depending on the origin, we would see very different cut costs. So this would be the amount of EPRPS consumed, which you could kind of associate to the amount of non-local gates that are established. As you can see, random circuits have really high costs on average for each technique. These are followed by real ones, and then generated circuits, so those coming from these instantiator machines, would have much lower cut cost. The amount of the cut cost found can kind of be related to the cost and the time that it would take to partition these things and the quality of the results in some sense. Now, the second thing that you could find very quickly from the results without getting to any conclusions was that there was a lot of variance, especially for random circuit performance. So some techniques, some partitioners could be really, really good or really, really bad within the same tests for the same network. This type of variance was less present in generated circuits, and it was present but less so again in real circuits. Now, I evaluated cut costs against the number of QPUs used and the circuit size, and as you can perhaps quickly see, random circuits are generally the ones that perform differently from everything else. Real ungenerated circuits can have similar structures and performance with obviously some differences. So as you can see, the circuit size doesn't exactly perform the same, but it doesn't start growing in the sense that it does in random circuits within generated circuits. It just oscillates quite a lot, but it still kind of stays continuous. Whereas random circuits start growing, and kind of similarly here we have slow growth in real circuits and generated circuits that's almost constant, but in random circuits you start having things moving more towards the higher cost as the number of QPUs grow with respect to where they start. So this kind of, in these graphs, you can kind of look at the shape of the data and see how differently it performs without necessarily worrying too much about the actual final cost, but rather just how the partitioners compete against each other. For instance, here we would have the greedy partitioner being the highest cut cost, whereas for both generated and real circuits, we actually have Fido-Mateus being the partitioner that costs the most. In random circuits, we have Kahipa being the lowest cost, whereas both in generated and real circuits, that is not the case. It's actually one of the worst partitioners. Now, the distribution of results again shows that random circuits show or demonstrate different performance or different results when compared to the real circuits. Generated circuits also differ, but they're still kind of within the same structures, even if not exactly the same as real circuits. They're slightly more accurate. What we can very clearly see, though, is that at least in the origins tested, it is not the same to test over random circuits and to test against, like, within real circuits. Now, the future of this research and this work for me is to basically continue studying if we can see that these structures that very clearly have some effect on what partitioners are better and what partitioners are worse can guide hypergraph performance in the sense in which we could perhaps characterize and exploit the structures emerging in DQC hypergraphs to minimize inter-QPU communication. So the main takeaways I would like to, to take away from this work is that random circuits can definitely lead us to believe that, or at least can lead us to believe, according to this empirical study, that some partitions are better than they would be in real deployment. They are not a fair baseline and they can misguide conclusions. Generated circuits can be more accurate and definitely a scalable solution for testing if we do not have access to real circuits or circuits that are instantiated from real implementations of quantum algorithms. And not only that, but they can be quite cheap testing benchmarks because the final cut costs that they show are much lower than even compared to real circuits. Thank you.